Verification and validation of embedded systems, the good, the bad, and the ordinary. My name is Cassie Dusute, and I am doing this project for ECE 554, University of Michigan Dearborn. My goal for this project include researching existing validation and verification methods, discovering which of these methods work and which of these don't, and propose a new process for verification and validation of embedded systems using those methods that work well. Some basic definitions you'll need throughout this presentation. Validation. Am I building the right product? Validation determines if the final software meets the needs and requirements of the user. Verification. Am I building the product right? Verification determines if the product has been built according to the design specifications and requirements. Finally, an embedded system is a combination of hardware and software that fulfills a dedicated function. For example, car airbags, microwave clock, or an alarm system. Verification and validation are two major parts of a product's lifecycle. Combined, they test that the product meets requirements and that the software and hardware are built correctly. For embedded applications, it is important that the systems pass verification and validation, not only for quality purposes, but for safety as well. Validation and verification should start early in the development phase. The cost of making changes goes up the further into a project you are, so the sooner you start validation and verification, the less likely you'll have to spend more money. Also, the use of an independent validation and verification team is recommended. This removes bias from tests and ensures high-quality products. During development, there are three fundamental concepts applied to achieve successful software. These three can often be confused for each other. Although they serve to achieve the same goal, they are all different and meaningful in their own way. Debugging is the process of diagnosing the nature of an already known error and correcting it. Verification proves that the program meets a given requirement. Testing is a process to identify any differences between the expected results and the actual. There is a current process known as the V-model lifecycle. This is used as a basis for many development processes. Verification and validation are done in parallel to each other. For every phase that's in the verification side, there is a matching phase on the validation side. There are two main types of validation and verification methods, static and dynamic. Here you can see the different types of static versus dynamic methods. For static, there's formal checking methods and critical path. Dynamic uses simulations and emulations. The main difference between static and dynamic verification methods is that static checks the design implementation for correctness without time constraints, while dynamic uses time to model the behavior. Static analysis is one of the static verification methods. It is more popularly known as code review. It analyzes the program without running it. Static analysis helps to uncover missing, redundant, deficient, or non-required functionality. It is best when used early on in development. There are two types of static analysis. A walkthrough, which simulates the execution of the object. It uses test data step by step to discover awkward algorithmic solutions. Then inspection, which is a technical review or a more formal code review. Formal methods, which are an abstract model of the system to be checked using math, are hard to use and require a certain knowledge of advanced mathematical techniques to use. Also, formal methods lack tools that a normal design engineer can use every day. One formal method is model checking. Model checking is an automated technique that, given a finite state model of a system and a logical property, systematically checks whether this property holds for a given initial state in that model. As you can see an example to the right that shows how the model checker works. It gets a system property and the system model, and if the property has been fulfilled, it notifies, and if it doesn't, it does a counterexample. Model checking explores the entire model to verify one single property. So for each property, it explores the entire model. This is a big problem because it could lead to state space explosion. It does, however, show the absence of errors, and it can be automatic. Another formal method is theorem proving. Theorem proving proves the correctness of a system by meeting a specific theorem. Theorem proving is more complex than model checking and is therefore rarely used. It only explores states needed to meet the theorem, but it also shows the absence of errors. A dynamic method is simulation. Simulation is easy to use and automate. It exposes erroneous behavior, but there is no guarantee on finding bad behavior. It is scalable so that large models can be simulated without the same problem as model checking, state space explosion. Prototyping and emulation. This is probably one of the best techniques used for verification. You have a close to actual product. It is executed in real-life speeds. It may be time-consuming and expensive as the design of the product must already be ready before the prototype can be built. However, you get the more accurate results with a prototype. Another important step in verification and validation is integration testing, especially for embedded systems, because you have to integrate the software and the hardware. There are many different types of errors discovered during integration testing. For example, wrong interrupt handling, inadequate timing, or interface errors for hardware and software. As a part of this project, I decided to take my own software lifecycle and improve it. Here I have defined product requirements, which is part of the research phase in respect. Separate hardware and software components, which is part of the prototyping phase. Separately do hardware and software development, which I will show you in the next coming slides. Integrate those hardware and software components. Validate and verify using the two methods that I will discuss later on. Release the product and maintain. The hardware development lifecycle is broken down into two pieces, whether you can contract out to another company or whether you keep the design in-house. Both of these require a review of the specific requirements before moving on. If you contract out, you may also have an option to hire another manufacturer, which later on in the presentation I'll just explain more. From there, you build the product to specs, you conduct certified testing with verification and validation, and then you move on to hardware-software integration. The software development lifecycle is very similar to hardware, however, it is most specific to software. You review requirements. If you need to contract out, you will follow the same steps, just with a contractor, same as in steps. You build your software architecture, model your code, generate your code and build, validate and verify your software, and then move on to integration. After reviewing the above methods, I chose two methods from each static and dynamic that proved to work the best. These are model checking, which is static and formal method, and prototyping. For the last part of my project, I decided to look into the current GM ignition switch recall and look to see where they went wrong. My goals and information that I would like to achieve. What was their test plan for the ignition switch? How were the known problems with the switch handled? What was the process for approving the switch? And what could they have done to prevent a recall? In my research, I found the GM validation plan, which includes the performance steps, tests here, and the validation tests located here. In the specification document, I found the torque requirements, or how much force was required to turn the key in the ignition for the ignition switch. As you can see, this states that the torque required to turn the switch should be between 15 and 25 Newton centimeters, with a plus or allowable tolerance plus or minus 5. In the validation report, there are many examples of the torque angle tests run, and like this, you can see that the tests did not meet the minimum requirement. In fact, only a handful of the actual tests passed. Now there was a process for approving the switch. Delphi, which was GM's contractor, has a production part approval process. The purchaser, which was GM, provides the design and specifications for a part. The part is built to specifications and tested against those specs. The results of the testing is then given to the purchaser for final approval. During the PPAP, Delphi had noted multiple times that the ignition switch did not meet GM's minimum torque requirements. In fact, only a handful of switches made it above the minimum requirement. So why was it approved? DiGiorgio, the engineer responsible for approving the faulty switch, approved the switch for production because he was not aware of any performance issues or effects on the safety of the car due to the underperforming switches. What could they have done to prevent a recall? While there are many ways a recall could have been prevented, I've narrowed it down to the two easiest solutions. Fix the faulty ignition switches so that they fell within the required torque range, or create better test coverage on how other components react when the ignition switch changes states. In many situations, verifying and validating a product could mean the world. In the case of an embedded system, it could mean someone's life. I have defined validation and verification, presented current methods and processes for each, and defined a new process and methods that seem to work best. I have also discussed the problem with GM's ignition switch and where they could have changed the outcome. These are my references. Thank you.